Welcome back to ECE 340. There's a lot of buzz. Must be an exciting afternoon happening today. We'll see. A few announcements. If you are available, I will be leading an info session on technical electives and the AMP, which is the Accelerated Master's Program, tonight in room ECE 530 at 5 o'clock. Another announcement, the LabVIEW, they're on a bus tour and they're going to plant their bus at Palm Drive. That's just north of 2nd Street. It's basically as you're coming out of the south doors of ECE, you would stumble into that bus if you were walking south, due south. Homework number 6 is due a week from today. Those are the announcements. Today what I want to do is pick up where we left off, and in order to do that I want to review this map or this picture of all these different system models that you can now create and how those are interrelated or connected. In particular, what I want to do after we look at that block diagram, just to sort of get our bearings straight, is to go one more direction and to take a transfer function and create a state space representation from that transfer function. We really won't do that process directly. We'll do it in an intermediate step. We'll take the transfer function to really a differential equation and then a block diagram and then a state space. So we're going to go quite a few steps between the transfer function to state space. The idea being that once you have this information, you could put that on your crib sheet, and once you're given a transfer function, immediately write down the state space representation. You'll see where those coefficients in the transfer function live or belong in your state space representation. That's the idea. We'll then look at some computations, and actually this is now relative to a different direction of model connections. If we have a state space representation, how do you find the transfer function? We just derived that last period, but you can do it many different ways, and I would like to show you the different ways so that you start to feel comfortable with wherever you're at. If you're on an island and have to do it in the sand with a stick, you can now derive that by hand, this 10 by 10 inverse of SI minus A. You're not doing anything else, right? You're just surviving. So you need to make sure that you can do this by hand. Yeah, the beach will be big enough. We'll show how to do it with a calculator. Because these new calculators can do symbolic, you might as well have a way of figuring out what's the answer in the back of the book. The calculator can basically do that as long as you don't have any numerical error entries. We'll then do it in MATLAB, and hopefully you'll start to see the different relationships. That's the idea. Once we have this system in MATLAB, we can start doing all sorts of simulations, and that's what I want you to feel comfortable doing. If somebody now gives you a system, whether that's a filter, whether that's a RF channel, a model of that, now you can put that into MATLAB and simulate it and tell them what's going to happen in their particular situation. That will lead us then into how do we build a system, and a particular system that you might want to build is a filter. So if you're on spring break and you're designing digital filters, this might be helpful. This I simply cut and pasted, and last time I told you that hopefully you can just pull this or extract this out of the notes and you don't have to frantically write it down. But if you're really paying attention, you should see a couple of features that weren't in the last iteration of this picture. And I've highlighted one. I didn't draw a line between the differential equations and the transfer function, and that line, you should be very comfortable going back and forth in that direction. And that's simply what's not on the screen. That's Laplace. That's just a Laplace transform away from each other. Is going from the differential equation, you should be able to Laplace transform that and obtain the transfer function, which is the ratio of y over y over x in this class. Or you can go the other way. And what we're going to do today is actually start with a transfer function, which is in the frequency domain. We will then transition into the time domain and find a differential equation relationship relating the inputs and the outputs, the y's and the x's. Once we have that differential equation, we'll put that into an all-integrator block diagram. We'll show how to transition or to re-express this differential equation in a block diagram form. Once we have it in a block diagram, it's pretty quick to find the state space. We're going to now go against this arrow, but we're actually going to do it in a different manner. It's basically a four-step process. That's the plan for today. And this is how that's going to transition. We'll first look at doing the transfer function to the differential equation. Then we'll take that differential equation and go into the block diagram. Once we have it in the block diagram, it'll be a straightforward process to identify the state space representation. That's the plan. So let's get started and work with a particular example. And this example is a little different. I wanted it to be slightly different than, let's say, the system that we had yesterday, but we'll come back to that, or on Tuesday. We'll come back to that system in a little bit when we were talking about this cascaded system of two RC networks. Suppose now somebody gives you this transfer function, the numerator being s plus 1 and the denominator being s squared plus 3s plus 6. Now, before we even go any further, even after a spring break period, can you tell me if this system is BIBO stable? Just by looking at it. And what was our criteria? If we have a second order polynomial, the roots of that polynomial will all belong in the left half plane if these two coefficients, the coefficient on s to the 1 and the coefficient on s to the 0, if those two coefficients are present and positive. They're present and they're both positive. We're assuming that the leading coefficient has been normalized to 1. So we're saying that this is a monic polynomial. Now, without even factoring it, if it's second order, you can immediately say, oh, that has roots in the complex S-plane, left half of the complex S-plane, without even factoring it, just by looking at that quadratic. So we know it's a BIBO stable system. Boom. Let's now go and find the differential equation for that. And that's simply going to require that we cross multiply. We'll multiply both sides by this denominator polynomial, and we'll multiply both sides by the input. And now we'll just get one equation in the frequency domain. Doing that, we end up with s squared plus 3s plus 6. That's now times the Laplace transform of the output. And then we said we were multiplying both sides through by the input's Laplace transform, and that's capital X of s. Once we have this, now it's immediate what the differential equation is associated with that system, because we can remember that when we multiply by s in the frequency domain, what does that correspond to operationally in the time domain? That's the derivative. Multiplying by 1s, that's one derivative. Multiplying by s squared, that's two s's, that's two derivatives. This now says that we have a differential equation y double prime of t plus 3y prime of t plus 6y of t is equal to x prime of t plus x of t. And that's now our first step. And I'm actually going to maybe relabel these. Maybe I should say this was A, B, and C, because I'm going to now call this first step the transfer function to dE. So if you're texting this, this is easier, TF to dE. And you could even replace that TO with a 2, right? So now you have, well, I thought for some reason that was TE and it was going to be a tight end and then we had a defensive end, but you're not going to, never mind. So this is TF to DE. We've just done that starting with the transfer function. Now what we want to do is we want to relabel this or rewrite this first by solving for the highest derivative of the output, putting it on one side and everything else on the right side. Solve for the highest output derivative. Meaning, now we simply have this y double prime of t is equal to minus 3y prime of t. And in anticipation of what I'm going to do next, let me go ahead and collect or sort of keep the derivative orders close to each other. I had a first derivative of x. Let me go ahead and put that next to the first derivative of y. And that's on the right-hand side. Then I have a minus 6y of t plus x of t. That's my second step in this process. Remember what we're trying to do. We're trying to go from a transfer function to a state space representation. Now what we want to do is we want to integrate this expression until we get y of t on the left. We want to just keep integrating this expression. Integrate to obtain y of t. Yes, we already have a y of t in the expression. We don't want to solve for that one. We want to solve for the highest power derivative of the output and then integrate both sides until we end up with y of t on the left. So now if I integrate that expression once, I have y prime of t is equal to minus 3y of t plus x of t, integrating those two terms once, plus an integral, and maybe I'll go ahead and reorder these so that I don't have to maybe forget that minus sign. Let's say this is x of t minus 6y of t. Since I now have to, oh, and maybe I should, if this is bothering you, let me just go ahead and change that and say this is x of sigma and this is y of sigma d sigma. That's now my first integral that's appeared. And I had a second order expression or a second order denominator. I should be expecting two integrators that are appearing in this expression. Now I want to integrate one more time to find or to isolate y of t on the left. And to do that, now what I want to do is actually nest these integrals, meaning now I have an integral. Let me say I have this now with a square bracket, and I'll say I have x of tau minus 3y of tau, and this is, I still have to now integrate this other piece, so that's still inside this integral, plus the integral of x of sigma minus 6y of sigma d sigma. Now I can close up that integral and say this is now d tau. Are we okay with what I did? I now have a nested set of integrals. Since I'm integrating both sides in a step-by-step way, the first integration allowed me to eliminate the derivatives, the first derivatives, but I had to integrate those undifferentiated terms. The next integration now said, oh, I'm integrating x and minus 3y, but I also have to integrate this other term that I just integrated. So that's going through two integrals, that little piece, x minus 6y. Now what I want to do is build up my block diagram based on this picture, or this set of equations. And I'm going to leave a little space underneath that because I'm going to add in some notation underneath that. What I want to do now is assume in my block diagram I have available to me the output y and the input x. Assume that I have those two signals available. If I have those, now I can build up this expression or this relationship out of x and y and some integrals and summing junctions and gain values. I want to now start with y of t, the output, and x of t, and build a block diagram. So I'm going to slide down a little bit, but sort of remember what I have. And what I said I wanted is I said I have available to me the output y, and let's just say up here is the signal x. And now I have those two signals available to me. Now I want to build up the relationship established by that earlier equation. Meaning, y of t needs to be the integral of the input minus 3 times the output plus the output of this second integral. And, well, I don't know when to really inject this information. What I'm wanting to do is I'm now going to, well, do you remember what we had for our block diagram before where the state variables appeared? Where did those, the inputs to the integrals, what did we use for the inputs to the integrals? Do you remember? Those were the derivatives, right? We had a q1 prime and we integrated it. Boom, the output of that integral was one of the states. The other integral had q sub 2 prime as its input. We integrate that. The output of that integral is q sub 2, the other state. To build this block diagram, what we want to do is assign state variables as the outputs of these integrators. And to make it, and our state space representation is not unique, but I'm going to, for maybe to make it cleaner, let me just say that this one, the output of that integrator, let me call that q sub 1. The whole thing. The output of this integral is q sub 1. And now I want the output of this integral to be q sub 2. Meaning now I can come in here and say that this piece right here is q sub 2. What have I done? Now I've said that right here, can I keep my color scheme? I'm basically saying y is q sub 1, aren't I? This is now q sub 1 of t. But q sub 1 is actually coming right out of an integrator. I'm just setting q sub 1 of t to be this entire right-hand side. So y of t is q sub 1. And that I said is what I had down below. Y is q sub 1. But now, if I go just inside this integral, everything in the square bracket is q1 prime. Does everybody see that? So if I go just inside the integral, this square bracketed expression is the derivative of q1 by definition of how we relate integrals and derivatives. So this is now, this piece right here is q1 prime of t. But what is that? What makes that up? Well, it's made up of a few terms, isn't it? It's made up of the input x. So I can now pull this x over. I said I had that available to me, and I can put that in to create a piece of q1 prime. q1 prime also was minus 3 times the output. And I can build that up out of a gain. I can just gain it up by minus 3, and I have it. Let me just go ahead and do that. I can now say, oh, this is now minus 3. I'll take y and put that in right there. I've now accounted for x. I've accounted for minus 3y. Now I just need to add in the output of the next integrator, and that's what I'm calling q sub 2. I just now say, okay, the other remaining term is now q sub 2 of t that creates q1 prime. Those are my three pieces that make up q1 prime. But q sub 2, I can find q sub 2 prime if I just slide inside that integral. Meaning q sub 2 was the output of an integrator, and now I need to build up q sub 2 prime. And what is q sub 2 prime? It's the input x. So I can now pull this input and put it right there. And it is minus 6 times the output. So I could now come and take the output, say minus 6. And now I have an all-integrator block diagram from my original transfer function. Yes, sir?
Is it not convention, I guess, to just pull a wire off the negative 3 plug and multiply that by 2?
So the question I think was, can I just come from the minus 3 point here that's just a little bit to the left of minus 3 and scale it by 2 and feed it in to this summing junction? Yes, you could do that. This is just easier because now you will be able to directly find the coefficients in your state space representation. So it's easier probably to not be mixing coefficients with products, not factoring your coefficients. Yes? Now, if you have initial conditions, you will have to then energize or establish these, let's say, state variables with some initial condition value, if that's what you're asking. If you now had a direct feed-through term, you might actually have the input coming directly in and feeding y to make up part of y. If you had a D, if you had a non-zero D matrix, you could have a path and that's where this direct feed-through comes from. That terminology is the input x is now directly coming in and being seen at the output y. And it might also have some filtered inputs and outputs with it. Yes? Yes, we're always going to assume that we have access to the output and the input. And everything that's in here, now you could just put a big block around this and say, this is my system. And I can't get into that. Maybe that's a car engine. Maybe you can sense some input to that. Maybe it's the fuel flow, and the output might be the RPM measurement of your engine. And maybe those are the only values or variables you have access to. And you're not going to assume, but now we have, because we have it modeled, we now have the internal dynamics identified in this block diagram manner. And so even the physical system, you may not have access to it. Now in your simulation, you can go off and say, oh, that's the internal pressure in my engine, maybe, depending on what this represents. Now, the fourth step, or I should say, I guess the fifth step, you could have done this creation of the block diagram without saying here's Q1 and here's Q2. You could now go in and say, oh, I know how to find a state space representation given a block diagram, meaning if somebody hadn't put these in, now what you would do, let's say on an exam I didn't label this and I just gave you an integrator with some gains and input and output. Now I say, give me the state space representation for that system. What you would do is you would label the outputs of each integrator as state variables and then build up your state space representation. And to be consistent with what we've done, this would then be Q sub 1, and this would be Q sub 2. Question?
So, sort of, back to larger scale thing. Notice that when a system with present and positive roots is stable, that seems to, here, translate to negative scale summing. Isn't that negative feedback?
So this is negative feedback. The question was when we were having the present and positive. Now this is just a second order system. If you get a higher order, then you can't necessarily directly make that necessary and sufficient, that condition of the coefficients being present and positive. But this picture is providing a feedback mechanism. This is being fed back. The output is being fed back and making up part of its output is an integrated part of it. Another piece is actually being integrated a couple of times before it comes in back to the output, and we have some feed forward paths from the input. So this shows you how the system is connected physically in terms of inputs and outputs. And yes, we do have some feedback paths in there. And you might have an unstable system and you want to stabilize it. That's okay. You can create this block diagram of an unstable system. Now you just have to figure out, how do I stabilize it? And that would be by introducing some additional feedback paths in this block diagram. But now that we have this block diagram labeled, maybe I didn't say the fifth step. The fifth step, let's just say, is now to assign state variables as the outputs or as the output of the integrators. Is it clear what I was trying to suggest? An exam problem might just give you the block diagram without labels on it other than the output and the input, and you might be expected to give me the state space representation. Then you would simply have to be doing step 5. Assign state variables to the outputs of the integrators, and then you would be able to write down the following equations. You should already be expecting this structure. You had 2 integrators, you better have 2 differential equations. And the standard form says that you have some matrix, which we've called the A matrix, times the state vector, plus the input vector. And this input could be more than just 1. Here we just have 1. It's a 1 by 1 matrix, x of t. It could have been, was it Michigan that we were saying our input was as far as its length? I think our states were Nevada, tall, and our outputs were Pennsylvania. Maybe I can remember 48 hours ago, but don't push me beyond that envelope. This is now our structure, but you can now pull those coefficients off from this block diagram. What is Q1 prime? Q1 prime, let me just see. Well, it's this, and what you might want to do is say, okay, with this summing junction, this is the output, and all the arrows going in are inputs. Let me just start right here and go clockwise so that I don't forget anything. Here's the first one. It's minus 3. Oh, that's Q sub 1. So this minus 3 is going to come and appear where? Here. Where does that live? Is it in the first matrix, which we call A, or is it in the second matrix, which we've been labeling B? It's in the system matrix A, and it's in location element 1, 1. Because it needs to now scale Q sub 1, and that's going to create part of Q1 prime. Now what do we do? Well, we're just going clockwise around this summing junction, and we come to the next one, and that's just Q sub 2. Where does that belong then in this expression? Does everybody see where those are coming from? This isn't difficult, it's just bookkeeping, right? But it provides you with a way to understand the relationship between the transfer function, the differential equations, the block diagrams, and the state space representation. We're not quite finished. We go just a little bit further to pick up the last one, and that one is just x. It could have been 4x if there was a gain in there. But this one just has a gain of 1, and there's the 1. Q sub 2 prime is the output of this summing junction, the leftmost summing junction, and now if we do the same strategy and go clockwise around that summing junction and add up all of the different turn arrows that are going in, we now have minus 6 y, but minus y is actually Q1. You may end up at some point having this being minus 6y, and you might have to then say, oh, y is actually 2Q1 plus 7 Q sub 2, and you would have to substitute that all in to get the proper coefficient. But in this case, y is just Q sub 1, and we can say that minus 6 is right there. Then we go around clockwise, and we end up and pick up an x. Okay, you're still awake? There. And what goes in the other location? There is no Q sub 2 directly feeding back to Q sub 2 prime. This is now your dynamical relationship, your internal dynamics of that transfer function that we started with. A representation. Somebody else might come up with a different representation, and this is not a unique way to run through and find the transfer function to a block diagram to a state space, but I found that the students like this approach right now may be the best. But there are other ways of going between those. The only thing remaining is now to write down the output equation, and we just had one output, y. That's supposed to be we had one output the C, the output matrix, will be 1 high. The D matrix will also be 1 high. And Y is now, we just go up to our block diagram and we look and see, oh, it's trivial, isn't it? It's just Q sub 1. But it could have been, there could have been maybe a different gain here. Maybe this was now 6, and this is now here, and maybe we even had, oh, this is getting kind of messy. Maybe we actually had a Q sub 2 feeding forward with a 4, and maybe we even had the input coming in here with a 7. Then Y would be 6Q1 plus 4Q2 plus 7X. Is that okay? Now can I remember to erase all of that so that people won't be thinking, where did that come from? But now it's fairly straightforward. Y is just Q sub 1, no Q sub 2, and no input X. And that's now our C matrix and our D matrix. Questions on that? Is that clear? Now, if you go back and start with this transfer function, you can actually see the 3 and the 6 appearing in your system matrix. They have a different sign, but here's the 3 and here's the 6 with a negative. And that 1 is always going to be there, and that 0 is always going to be there, the way that we built this particular process. Then our numerator was 1s plus 1, and that's where those two 1s come from. And the output structure is just always going to be this 1, 0, 0. If you have a strictly positive transfer function, meaning the numerator is strictly less than the denominator. So you could, by inspection, go directly from, and not go through all of this, that transfer function directly into a state space representation. But on your homework, you're going to need to go through this, and I think it's helpful to go through the steps so that you kind of get comfortable with this process. Questions on this? This now allows you to connect up all of the different pieces in that structure of the different models of a system, in the frequency domain, the time domain, etc. Let's now look at some ways to make some computational results. And for now, let's go ahead and return to this path of taking a state space representation to a transfer function. And the state space system that I want to begin with is from the RLC circuit that we had on the 19th. We had, in this example, our A matrix was minus 1.5, 1/2, 1 minus 1. Our input matrix was 1, 0. Our output matrix was minus 1, 0. And our D matrix was 1. We only picked one output in this particular example. And that was this cascaded combination of two RC networks. Do you remember what the expression was to find the transfer function g of s in terms of the state space matrices? Do you remember what that formula was? And you could write this down on your sheet of notes. So we had the C matrix, the output matrix, times SI minus A. There's the system matrix A. We invert that whole mess symbolically, times the input matrix B, and then we add in, if it exists, the direct feed-through matrix D, and that's our transfer function G of S. Let's do this by hand, just so you kind of see what might be going on. If you just keep doing it with your calculator and your MATLAB, maybe it's not clear where these are coming from. But in this, if you have done it in linear algebra, maybe they didn't explain that all of this could be applied to a circuit. Here's SI minus A. S is our frequency variable. How big is I? And I is the identity matrix. It's compatible dimensionally with A. There's SI. And now we need to subtract the A matrix, which was minus 1.5, 0.5, 1, and minus 1. And I'm going to do this in a lot of different, or in many different steps so that you just see what's going on. There's SI again. And now I could go ahead and push that negative sign through and say there's a 1.5 minus a half, here's a minus 1, and there's a 1. Which, if I now look at SI minus A, I can now combine those two 2x2 matrices, and I have S plus 1.5. That's in the 1, 1 entry of the matrix. Then I have a minus 1/2 in the 1, 2 entry. In the 2, 1 entry, I have a minus 1, and in the 2, 2 entry, I have an S plus 1. Again, that's just a 2x2 matrix. Now what I need to do in that expression is I need to find the inverse of that matrix. And you probably all remember that the inverse of a matrix is the transpose of the matrix of cofactors. Maybe you don't. Well, then you have to divide by the determinant, don't you? So the first thing we want to do to get this inverse is say, let's divide by the determinant. So now I'm going to say 1 over the determinant. And the determinant, we're going to just keep using that, but that's the product of the diagonal elements minus the product of the off-diagonal in this 2x2 matrix. I now have S plus 1.5 times S plus 1 minus a minus 1 times a minus 1/2. That's the determinant. And that's a polynomial that's always in the denominator of this SI minus A inverse matrix. Now I'm running out of room. But now I need to build up this matrix of cofactors, and don't forget that I'm, after the fact, going to transpose it. First thing that I do is I say, okay, I need the cofactor associated with the 1, 1 entry in this matrix. It's the 1, 1 entry. That's critical. So you basically say, let me eliminate the first row and the first column and take the determinant of what's left over. And I'm going to scale that by minus 1 raised to the 1 plus 1 power, where the 1, 1 is the 1 plus 1. And what's the determinant left over if I remove the first column and the first row? What's the determinant of what's left over? In this case, it's a scalar, so the determinant of a scalar is just the scalar. If it was a matrix, you would take the determinant of the matrix that's left over. This is falling out rather easily because it's only a 2x2 matrix. But now I need to multiply this by S plus 1. And that's my 1, 1 entry. You know what? I'm going to cheat. I'm going to use my infinitely wide paper. I didn't get too much wider, but let's build up. Let's just play kind of fast and loose. Let's find this guy next. So this is going to be scaled. Whatever we end up putting down here, it's going to be scaled by -1 raised to what? The 2 plus 2. Second row, second column. That's where that exponent comes from. This is now going to be -1 raised to the 2 plus 2. And what's it going to multiply? It's now the 2 entry. I remove the second row. I remove the second column, and I take the determinant of what's left, and that's this s plus 1.5. Yes, sir? Yes, there's a trick for 2 by 2 matrices, and let's see if we can see the trick after we go through this laborious process. Okay? But that trick only works for 2 by 2 matrices. It doesn't work for anything else. So I'm trying to show you the generic process, although this explodes a little bit when you get higher dimensions. But your calculator can do all of this for you. If you have a 4-function calculator, it will do this symbolic matrix algebra. No, it won't. But on the homework, you can use your high-powered calculator. And you can use it on the exam too, but hopefully I won't make the exam so that you have an unfair advantage over me that's in the back row trying to do my 4-function calculator analysis with this. Okay? Where were we? Let's do this one. Now I have a -1 raised to what power? I'm in the second row and the first column. So this one makes a difference, doesn't it? Now that -1 is raised to the third power. That's going to negate whatever I put next to it. Now I'm going to take the determinant of what's left when I remove the second row and the first column. And that's -1/2. Up here I have -1 to the 1 plus 2. I remove the first row, I remove the second column, take the determinant of what's left, and I have a -1. And if we do all the algebra, the determinant becomes s squared plus 2.5s plus 1.5. What's that? -1/2. So I end up with s squared plus 2.5s plus 1. If my memory is working. So I have s squared plus 2.5s plus 1. That's what simplifies in the denominator. And now over here, the diagonal pieces, when I transpose that matrix, they don't move, do they? And they don't get scaled by a negative number because they're 1 plus 1 and 2 plus 2. That's -1 to an even power. This is pretty easy then. S plus 1 and S plus 1.5. The off diagonals will change. Let me look at what's going to appear here. Well, that's going to be whatever is down here. Once I transpose it, I have -1/2 -1. So now that 1/2 pops up here. And finally, down here, this is going to be coming to me from the 1, 2 entry. That's going to be -1 times a -1, or a 1. And now you might be able to see the relationship that somebody said, isn't there a shortcut for all of this? There is SI minus A right here. And if we wanted to find the inverse of that, what we do is we take 1 over the determinant, and then what do? we flip the diagonals and change their sign, and then, I'm sorry, we flip the diagonals and change the sign of the off-diagonal terms. That's the relationship, or this 2-by-2 trick. And you can do that on an exam or homework if you want. You don't have to go through all of this, or you can let your calculator do it. But now we have, if we let, instead of me writing that determinant all the time, let me just say there's delta. Now we can rewrite SI minus A inverse as S plus 1 over delta of S, 1/2 over delta of S. So now we have 4 transfer functions, don't we, in SI minus A. Here we have 1 over delta of S, and down here we have S plus 1.5 over delta of S. That's now SI minus A inverse. We went through all of that because we need this symbolic matrix in our expression for the transfer function g of s. Bless you. So now g of s is c si minus a inverse b plus d. And C was a matrix -1, 0, wasn't it? That was our C matrix. Our Si minus A inverse matrix, now we just have, is S plus 1 over delta. This is 1 over delta. This was 1/2 over delta, and this is S plus 1.5 over delta. That's times B, which is 1, 0. Plus the d, which is 1. We can perform this matrix multiplication either from the left or from the right. Since this one doesn't have a negative sign, it's easier in my head. What does this, post-multiplying this 2-by-2 matrix by 1, 0 going to do? That's just going to take this first column, isn't it? And I still have that matrix, but now I can write this a little bit cleaner and say I have -1, 0 times S plus 1 over delta, and here's 1 over delta, plus 1. And now I have a 1/2 times a 2/1. Good, it's a 1/1, which is what I better have. I need a scalar transfer function since I had 1 input and 1 output. If I now do this multiplication, ooh, my deltas look like S's, don't they? So make sure you're maybe a little cleaner with your handwriting. My second grade teacher won't be very happy. This is now minus S plus 1 over delta of S plus 1, and that's g of s. And if you simplify this and put it all over a common denominator, you will end up with s squared plus 1.5s. Hopefully, doing the algebra. Questions on that? Now, maybe we want to do this with our calculator. Whoa, what happened to this beast? Oh, I guess it's okay. All right. So now, what I want to do, let me kind of do this in stages. Let me input my A matrix. And what was that? That was now a matrix. It's 2 by 2, and it was -1.5, comma, and it was a half in the first row. Then I follow that with a semicolon. Then what was downstairs? Was it 1? And then minus 1? That's now my A matrix. And if I want to tell my calculator that I want that stored as A, I can actually store that as a variable. Or I could just enter that and just go up and capture it all the time. But let me go ahead and say, let's store that, control store as A. Whoops, where was A? What? Now I've lost track of what I was doing. This was 1 minus 1, wasn't it? Oh, you know what? I bet this silly thing is going to really go crazy. Let me do... Now A is stored as our A matrix. And we don't know that unless we kind of keep track of it. What else did we have? We have a C matrix. Well, we could even, if we opened up our manual, what in the world? Now if I wanted to maybe do the eigenvalues of that matrix, there's EIGVL, and let me just say that's eigenvalues of A. Maybe I need that at some point. That's now minus 2 and minus 1/2. Good, they're in the left half plane. That makes sense. So I haven't done anything that makes me feel like I've messed up just yet. So now I have A and I have my eigenvalues of A if I need those later. Let's now create our output matrix C, which was minus 1, 0. And now I have to remember how I did this. Let me, say store that into C. And I need my input matrix, and that was 1 semicolon 0 to give me the column structure of B. Let me store that in B. And there's my B vector. And what else did I have? I could go the old school and say D. D was 1, wasn't it? I could always just type in 1, but I'll just play since I'm playing here. And there's D. Now what I can do is, well, I can do this many different ways. Maybe to start with, I want to, what do I want to do? Let's just play a little bit. Now here's S times, let's do this times the identity. I can say 1, comma 0, semicolon 0, comma 1. And now let me say minus A, and let me go out here and say, why don't you raise that to the minus 1 power? And now that should be our SI minus A matrix that we had before. Does that look similar to what we had? All the denominators better be the S squared plus 2.5S plus 1, and our numerator expressions better be what we calculated by hand. We wouldn't have had to do that intermediate step. We could just say C times, and you might actually want to do something different than input this identity matrix the way I'm doing now by longhand all these times. But there's SI minus A, and A is bold. It seems to know that, oh, that's something in memory. Minus 1, now times B, but we want that plus D, didn't we? And now that's our transfer function, G of S. 1 minus that mess, which is what we had before. But if we wanted to see it as a compressed transfer function, one way of doing that is to, let's just say, I wanted to do complex factor. Where is that at? There it is. So now if I do complex factor, because let's say I hadn't already found that the eigenvalues were real, and I didn't know what they were, I'm going to assume they're maybe complex. Let me say complex factor, go up and capture that expression. And now there is my transfer function written in pole zero form. In factored form, I have s squared plus 1.5s all over s plus a half, that factor times s plus 2, and that's consistent with where my eigenvalues are. That's now how I could do it for or with the calculator. Let's now play with this in MATLAB. So here we go. A was what? A was our minus 1.5, 0.5, 1 minus 1. Is that what we had for A? B was 1, 0. C was minus 1, 0. Whoops. And D was just 1. Now what I could do is I could say, let me define an object, I'll call it system 1, as a state space representation. So that's equal to SS. And did I use lower or uppercase? So I said that was A, B, C, D. What? What's wrong?
That's cheating.
That's cheating? Well, not in class it's not. So this is now our state space representation. And if you want it in a transfer function, MATLAB is quick to do that. You can say, you know what, let me call that system1 transfer function just to make it unique and say TF sys, or did I call it sys1? I called it sys1. And there's now my transfer function. Pretty quick, huh? S squared plus 1.5s over S squared plus 2.5s plus 1. Now what do I want to do? Well, maybe I want to do some simulations, right? Or what do I want to? Oh, we could do Bode plots. We could do all sorts of things, couldn't we? I've got too many notes here telling me what I want to do or not do. We could check that our calculator was working and say, what are the eigenvalues of A? That's consistent. And maybe we just wanted to quickly see what this system might do in a step response. We might just say, what's the step response of system 1? Without doing hardly anything, MATLAB will just honor our request and give us a step response. And does that make sense? We inject 1 into that system, which the system was this s squared plus 1.5s over s squared plus 2.5s plus 1. Now, would we expect that kind of step response? We command it to go to 1, and after a transient, it dies out. And remember what that output was. That was the current coming out of this RC circuit supply. So we have a voltage source that has a 1 volt, and that's charging up these 2 capacitors, isn't it? What's going to happen to your current? It'll stop flowing, won't it? Once those capacitors charge up, and they're going to charge up with this e to the minus 1/2 t and e to the minus 2t structure. That's based on our eigenvalues. Pardon? The eigenvalues are directly related to the time constants. Now we have to look at their reciprocals to see the time constants. Since these are real, that's pretty nice or easy to do. So let's now I've lost my pen. All right, got too many things going on here. Having too much fun. What if we want to simulate this? Let's say that somebody says, you have the system, so now we're with MATLAB, And we have our system 1, but we want to let the input, x of t, what do we want that to be? Let's say that that's 2 times the sine of 6t. And now on the exam I say, okay, you have your system. Either I give it to you as the transfer function or I give it to you as a, b, c, and d. And I give you this input x, and I say, tell me how fast you want to sample and how long do you want to sample in a MATLAB simulation. That's a valid exam question. So how fine do you chop this up? What's your delta t? And how long do you simulate? And what do you expect to happen out of this system? We have a linear system, don't we? And it's stable. And we're injecting a sine wave. So we're going up and shaking it, aren't we? It's probably oscillating a little faster than that, right? No, what is its frequency? 6 radians per second, right? So what is that frequency? 1. So maybe I was a little fast with my shaking. Okay? All right. So what do we do? If you're now simulating this in MATLAB, how fast do you sample? And the duration of the simulation. What influences the answers to these questions? How fast do we sample? Have we already somehow learned a little bit about this system? What did we already do? We already found the eigenvalues of A, didn't we? And they were -1/2 and -2, which means that those give rise, if you just walked up and kicked your system, you kind of hit it with an impulse, you're going to see that system naturally display the following modes. What will they be? What will the modes be of the system response? One is coming through the first eigenvalue, e to the -1/2 t, and the other one is the other one, e to the -2 t. You will see that system naturally want to shake with these exponential decays. And now from this, you can find the time constants. The time constants are just what makes that exponent equal 1 in both cases. Here, we would say, oh, I have 1/2, let's say tau 1 equal to 1. And tau 1 now is equal to 2. So this is maybe a bad example because they're the reciprocals of each other. Should have changed it. Does everybody see that? This one now is saying 2 tau sub 2 is equal to 1, and tau sub 2 is 1/2. Now, which of these? Well, this is now the slow mode, isn't it? A longer time constant, and this is the fast mode. And if we're worried about how fine we chop things up, which of these do we focus on? The fast one. To figure out the duration or how long the transient is going to be, which one do we focus on? The slow one. So they're both important, aren't they, to our answers? But if we want to see how fast do we chop, we not only need to worry about the natural behavior of our system, which is influenced by the eigenvalues, but we also need to know how fast are we shaking it. We have to consider both pieces. From our system piece, our system now says that, oh, if we just based our sampling on the system, we would maybe take this t sub 2, the fast one, and divide it by 10. So now we have 1 over 20. Is that 0.05? Now if we looked at our input, what do we know about that? Well, we know that the input had a damped frequency of oscillation of 6. It was 2 sine of 6t, wasn't it? And this is now 2 pi f sub d, and you just told me f sub d was roughly 1, which it is. Or this is now 2 pi over t sub d. And we now know what the period of that input waveform is in terms of duration. We just solve for t sub d, and that's going to be 2 pi over 6, or approximately 1. That's how long it takes to make one period of the input sinusoid, 1 second. So what? We're trying to sample this. What does that mean? Does that influence how fast we chop this up? What do we say we do with damped frequencies when we want to chop up our time axis? Rule of thumb, 30 or 60, right? 30 to 60. Let's just do 30. So now we say t sub d divided by 30. We now have 1 over 30. Well, that's kind of an ugly number. So let me say that this is 100 roughly divided by 3, 1 over 33. So I'm making it smaller. And that's now 0.03. So now, how do we sample? We take the minimum of those two, don't we? Or even less. And now the input is determining how fine we chop up. That's needing to be resolved better than the exponents in our natural decay of our system. Now, how long should we sample, or what's the duration of our simulation? If we just had a natural response, what would the duration be? If we just kick the can, and we can cheat, can't we? How long should we simulate this? This was exciting the system, wasn't it? With a step input. So I would have been going the whole distance, but I see some backpacks and I didn't want to trip over them. That would have been an input, a constant input. And what was our slowest time constant? 2 seconds. And how many of those do we worry about? 5. So this seems to say, oh, our transient's 10 seconds long, and that's consistent with the step response, isn't it? But what did we say we're shaking it with? 1001, 1002, 1003. An input waveform that was sinusoidal. So this one's not going to die, is it? The transients will disappear after 10 seconds, but after that we'll hit sinusoidal steady state. And we may want to see a couple periods of that sinusoid after we've seen the transient decay, so that now we might say, okay, we want the duration to be 5 times tau slow plus, let's say, 2 t sub d, roughly. And this was about 10, and this was about 2, so let's say that our t end is 12. Is that okay? All right, now we can quickly do this. You thought that it was cheating before. Now it's really going to be cheating. Let's say 0 time, and you know what? I'm going to make this a little bit finer. We needed to be 0.03 or less. 0.01 is easy to type. And how long did I say to 12? So there's our time. Our input x was it 2 times sine of 6, of 6 times time. And I don't want to display all that time. Then I need to simulate this, so I'm saying my output y is going to be a linear simulation, LSIM, of system 1, that's my system, excited by the input x, and the input has to be the same vector size as my time vector. And now I've simulated, if I hit enter, that's now my output y. I can now say, oh, let me put this in a new figure window and say I want to plot time and y. This one is kind of hard to see the transient, but you can sort of see it, can't you? With this particular transfer function. And we hit steady state roughly at 10 seconds, and then we move on from there. Questions? We'll pick up at that point. Go Wildcats, and we'll see you next Tuesday. Or tonight if you're interested in the Tech Elective AMP conversation.